Tonight, one of the strangest stars in our galaxy may finally be giving up the thing it has been hiding. For more than a decade, this star has faded in ways that seemed almost impossible. Its light has dropped suddenly, deeply, and without a clean rhythm. Dust became the best explanation for the darkness, but dust only moved the mystery one step backward. What was making so much of it, and what was throwing that material across our line of sight? By the end of tonight, we are going to follow a new clue that may connect those pieces. Evidence for a massive, unseen companion orbiting the star, an object that could be several times heavier than Jupiter and powerful enough to disturb smaller bodies around it. If you enjoy calm journeys into the mysteries hiding inside real astronomical data, subscribe and stay with us. Now, let's begin. You are looking towards Cygnus, the Swan, into a crowded field of stars more than 1,000 light-years away. Nothing there appears dramatic to the eye. One faint point is too dim to see without a telescope. It looks ordinary. That is exactly why what happened next became so unsettling. The star is called KIC 8462852, better known as Boyajian star or Tabby star. It is hotter and somewhat larger than our Sun. But those basic facts are not what made it famous. The trouble began in data from NASA's Kepler space telescope. Kepler watched stars for tiny drops in brightness. Usually, the pattern is simple. A planet crosses in front of its star, blocks a small amount of light, then comes back again after completing another orbit. You see a dip, then another, then another. The timing forms a clock. Tabby's star refused to behave like a clock. Its light dropped by wildly different amounts. Some dips were small, others reached roughly 20%. Imagine watching a bright lamp and seeing 1/5 of its light disappear, not because the bulb is failing, but because something enormous has moved between you and the lamp. Then imagine waiting for that shadow to return on schedule. It does not. That missing rhythm changed everything. A normal planet could not easily explain dips this deep and this irregular. A collision was considered. Clouds of comets were considered. Material around the star was considered, and because the pattern was so unusual, one speculative idea escaped astronomy and entered popular culture. Perhaps an advanced civilization had built giant structures around the star. It was an extraordinary possibility. It was also never the leading physical explanation. As astronomers collected light at different colors, a more grounded clue emerged. The star did not dim equally at every wavelength. Blue light was reduced more strongly than redder light. A solid object should block colors more evenly. Fine dust does not. Dust scatters and absorbs shorter wavelengths more strongly. So the shadow had texture. That was a major step. It pushed giant solid structures away from the center of the story and put dust in their place. Yet the dust created a new problem. Dust is not an answer unless you can explain the dust. Around a star like this, very small grains are fragile. Radiation pushes on them. They spread, drift, or get blown away. If fresh clouds repeatedly cross the star, something has to supply those clouds. You need broken objects, collisions, evaporating bodies, or some other process that keeps placing material into the right orbits. For years, that hidden machinery remained uncertain. Then another telescope looked at the same star. TESS, NASA's Transiting Exoplanet Survey satellite, observed Tabby's star across several sectors. Researchers later reanalyzed about 160 days of those observations. Inside the data from September 3, 2019, they found something that did not resemble the famous jagged dips. This event was smooth. For about 21 hours, the star's light fell by roughly 1.1% and then returned. The shape was rounded and strikingly symmetric. Instead of a torn cloud producing a messy shadow, this looked much more like one large object moving cleanly across the face of the star. Picture the difference. The old dips were like smoke blowing across a headlight. This one looked more like a dark ball crossing a lamp. And that single shape reopened the entire mystery. A 1% dip does not sound dramatic beside a 20% collapse. But the shape matters as much as the depth. A smooth, U-shaped transit is the kind of signature astronomers search for when a solid body passes in front of a star. The researchers tried to make streams of exocomets reproduce it. The models struggled. They either fit poorly or required conditions that became physically difficult to justify. A large companion gave a cleaner explanation. But one transit is a dangerous clue. If you see an object cross once, you know it passed in front of the star. You do not automatically know how long its orbit takes. It might return in a year, 3 years, 10 years. If later observations miss the exact crossing, the period can remain hidden. So the team worked backward. They compared the TESS event with years of earlier Kepler observations and other brightness records. If the object had crossed during times when those telescopes were watching, another similar event should have appeared unless it landed inside a gap or was buried inside one of Tabby's deeper dips. That eliminated huge stretches of possible orbital time. Only a handful of windows survived. The shortest allowed periods are a little over 1,000 days, nearly 3 years. And when the researchers combined the light curve with measurements of the star's motion toward and away from us, another clue appeared. The star itself may be wobbling. Not dramatically, not enough for your eye to see, but gravity does not allow a massive planet to orbit a star without pulling back. The two bodies move around a shared center of mass. We usually imagine a planet circling a fixed star, yet the star also makes a smaller loop. Measure that motion carefully enough, and an invisible companion can reveal its weight. The current fit points towards something around 9.4 times the mass of Jupiter, with a radius near 1.7 times Jupiter's. The uncertainty is large, and the detection is only at about 2.3 sigma. That means we should not call this object confirmed. But if it is real, it is enormous. It may sit in the grey territory between a giant planet and a brown dwarf, a class of objects too small to shine like ordinary stars, yet far heavier than the planets in our own solar system. And suddenly the story of Tabby's star changes. The question is no longer only, what is blocking the light? A deeper question appears. Could this massive companion be the unseen hand that has been stirring the system all along? Because a giant object does more than make one clean shadow, over long periods, its gravity can tug on smaller bodies, stretch their orbits, scatter them inward, and send icy or rocky debris toward dangerous paths. If those bodies begin to break apart near the star, they can create dust. And dust is exactly what the older dips appear to require. So we now have two kinds of shadows, chaotic dusty ones that made the star famous, and one smooth event that may belong to something much larger. The next step is to find out whether they are separate accidents or parts of the same machine. If those two shadows are connected, gravity is the bridge. A giant companion does not need to touch a comet to change its future. It only needs to pass close enough, often enough, for tiny pulls to accumulate. One pass can stretch an orbit, another can tilt it, a later encounter can steal a little orbital energy or add some. Over thousands or millions of years, a body that once moved safely through the cold outer system can be pushed onto a path that dives toward the star. You can picture a wide ring of icy rubble circling far from the heat most pieces may spend their entire lives doing almost nothing dramatic. Then place an object several times heavier than Jupiter inside or near that population. Every time a smaller body approaches it, the giant becomes a moving gravitational slingshot. Some objects are thrown outward, some are trapped into new rhythms, and some are sent inward. That last group matters here. As an icy body falls toward an F-type star like Tabby's star, the heat rises fast. Frozen material can turn directly into gas. Dust can peel from the surface. If the object is already cracked, spinning, or weakly held together, the close approach can make the damage worse. Instead of one clean, solid body crossing the star, you can end up with a train of fragments wrapped in expanding clouds of dust. Now the old light curve begins to look less like a random collection of accidents The deepest Kepler events did not behave like the transit of one planet. They were irregular, sometimes complex, and could stretch across days or much longer episodes. The original discovery paper already pointed toward families of fragments as one of the least bad ways to explain that behavior. Later observations strengthened the case that the blocking material contains small dust grains rather than one opaque solid screen. But the new companion idea adds something those dust models were missing: a driver. The 2026 study does not show a giant object physically breaking comets apart. It does something more limited and more interesting. It finds a single smooth TESS event that is difficult to reproduce with an exocomet model. And it finds tentative radial velocity evidence for a massive companion at an allowed long orbital period. The authors explicitly connect that possibility to an older idea in which a planet perturbs comet-like bodies onto star-grazing orbits. That distinction is crucial. We have not found the machine in operation. We may have found one of its gears. Suppose the candidate really is around 9 Jupiter masses. Jupiter already dominates the architecture of our outer solar system. It bends the paths of comets, captures some objects into resonances, ejects others completely, and changes which bodies can reach the inner planets. Now imagine an object several times more massive, moving through another planetary system on an orbit that takes at least about 1,030 days. You would not need it to produce a spectacular event every orbit. Gravity can work quietly. A small body may circle hundreds of times before a resonance slowly pumps up its eccentricity. That word sounds technical, but the picture is simple. Its orbit becomes less like a circle and more like a stretched rubber band. The far end moves farther out. The near end drops closer to the star. Closer means hotter. Hotter means more gas and dust. And more dust means deeper, stranger shadows when the geometry lines up with us. This also helps explain why searching for a neat repeating pattern can fail. The giant companion itself, if it transits, should eventually repeat on a stable orbital clock. The dust it helps create would not have to. Individual fragments could occupy slightly different paths. Their clouds could grow, shrink, spread, collide, or disappear. One swarm might cross our line of sight. Another could miss the star completely. One cause can therefore produce many different-looking shadows. That is a much more useful idea than asking one object to reproduce every dip. There is another complication, though, and it makes this system even richer. Tabby's star already has a known stellar companion far away. High-resolution imaging and years of astrometry showed that a faint neighbouring star moves through space with it. The pair are separated by roughly 880 astronomical units in projection, about 22 times Pluto's average distance from our Sun. Researchers have suggested that this distant companion could also disturb bodies around the primary over very long timescales. So if the new candidate survives confirmation, Tabby's star may not have one gravitational troublemaker. It may have two. One would be a distant star applying a slow, broad tug to the architecture of the system. The other would be a much closer giant planet or brown dwarf capable of strongly reshaping the paths of smaller bodies. We should be careful here. That two-stage picture is a possibility, not a demonstrated history. The wide companion is real, but its exact role in the dimming remains unknown. The closer giant is not yet confirmed at all. The radial velocity signal is only tentative, and the 2026 team says more measurements are required. Still, the architecture is suddenly worth imagining. Far from the star, a second sun crawls around on an enormous orbit. Closer in, a dark giant may circle every few years or longer. Between them could lie reservoirs of smaller bodies whose paths are being slowly rearranged. Then, occasionally, one of those bodies falls. It heats, it fractures, it sheds a veil, and from more than 1,000 light-years away, all we see is the star blink. That gives the famous dips a physical chain. Gravity changes an orbit, the orbit brings material inward, heat or disruption creates dust. Dust crosses our line of sight, the star fades. Every link is familiar physics, None of it requires a new force, an exotic material, or a machine built by anyone. The mystery is whether those links actually belong to this system, and there is a way to attack that question. If the smooth 2019 event was caused by a real companion, then that object must come back. Its orbit cannot hide forever. The years of Kepler, TESS, ground-based photometry, and radial velocity measurements already remove large portions of the calendar. According to the 2026 analysis, only 5 period windows remain possible before follow-up observations narrowed the first 2. That turns a strange one-time shadow into a prediction. Somewhere ahead, there should be another crossing, another gravitational wobble, or eventually an astrometric motion that exposes the orbit directly. And the most powerful test may not come from watching the star dim at all. It may come from watching the star move. The most revealing thing in this system may not be the shadow at all. It may be the star's motion. Every orbit is a two-body dance. We usually draw a giant planet going around a star, as if the star were nailed to the center of the page. In reality, both objects circle a shared center of mass. If the companion is tiny, the star's motion is tiny. If the companion is massive, the star is pulled into a larger wobble. You cannot watch that wobble directly with your eyes from more than 1,000 light-years away, but you can measure one part of it through the star's spectrum. When the star moves slightly toward us, the dark absorption lines in its spectrum shift towards shorter wavelengths. When it moves away, they shift toward longer wavelengths. Astronomers translate that back and forth motion into radial velocity. The idea is beautifully simple. You never need to see the hidden object. You watch what it does to the star. For Tabby's star, this is especially useful because the proposed companion is not small. The 2026 analysis combined archival radial velocity measurements with new observations and found a tentative signal compatible with the same long-period object suggested by the 2019 TESS transit. Their preferred fit corresponds to about 9.4 Jupiter masses, although the uncertainty is large and the statistical significance is only about 2.3 sigma. The authors therefore treat it as evidence worth following, not as a confirmed detection. That caution matters. A 2.3 sigma signal can disappear as more data arrive. Stars are noisy. Instruments have offsets. Different observing runs use different spectrographs, different calibrations, and different sampling. A long-period companion makes the problem harder because you may observe only a small slice of its orbit. Instead of seeing a clean repeating wave, you might see only a slow rise, a bend, or a shallow fall. Imagine trying to prove that a Ferris wheel is turning when you are allowed to photograph it only a few times over several years. You might catch one cabin slightly higher in one image and lower in another. That is useful. It is not the same as watching a full rotation. This is why the transit and the radial velocity clue are stronger together than either one is alone. The transit says that something large may have crossed the face of the star on September 3, 2019. The velocity measurements ask whether the star is being pulled by an object moving on a compatible orbit. The 2026 team then used earlier photometric coverage to rule out periods that should have produced another visible transit. That left a limited set of possible orbital windows, all with periods of at least about 1,030 days. So the hiding place is shrinking, not spatially, temporally. Instead of asking, is there something somewhere around the star? We can begin asking, if this object is real, when is it allowed to return? That is a much more dangerous question for a hidden companion, because an orbit makes promises. If the 2019 event was a true transit, the object cannot simply choose never to appear again. It must keep moving. Once its period is known, future conjunctions can be predicted. Even if the geometry changes slightly or observations miss one crossing, the gravitational pull on the star should still persist. And there is another method waiting in the background. Astrometry. Radial velocity measures motion toward and away from us. Astrometry measures motion across the sky. Instead of watching spectral lines shift, astronomers track the star's position with extraordinary precision and look for a tiny sideways deviation from the path it should otherwise follow. Think of a person walking in a straight line while a heavy dog keeps tugging on the leash. From far away, you may not see the dog, but the person's path gives it away. Gaia was built to measure stellar positions and motions on this kind of scale, and the 2026 study specifically identifies future Gaia DR4 astrometry as a way to test the nature of the proposed object. A sufficiently massive long-period companion can leave an astrometric signature that complements the radial velocity signal. That could be decisive because the two techniques see different directions of the same dance. Radial velocity tells you how fast the star moves along our line of sight. Astrometry tells you how it shifts across the sky. Put them together with a transit, and suddenly geometry begins to lock into place. You can constrain the orbit, inclination, and true dynamical mass far better than with one method alone. That last part matters because mass is where the identity of this object becomes interesting. The best fit value sits near 9 Jupiter masses, while the 3 sigma upper limit in the 2026 analysis extends below about 28 Jupiter masses. Combined with the transit-derived radius of roughly 1.7 Jupiter radii, the candidate lands in the broad regime where astronomers start asking whether they are looking at an unusually massive giant planet or an object approaching brown dwarf territory. Those labels sound neat. Nature is less neat. A brown dwarf is not simply a failed star in the way popular diagrams sometimes suggest, nor is every object below the hydrogen-burning limit automatically a planet. Formation history matters, mass definitions overlap, and the boundary can become messy. For our mystery, the useful point is simpler. Whatever this candidate is, it would be massive enough to exert serious gravitational influence on surrounding debris. If it exists. That phrase has to remain attached to everything, because the history of Tabby's star is full of ideas that once sounded exciting before the data narrowed them. The star became famous precisely because unusual observations invite unusual stories. But astronomy advances by making those stories vulnerable to tests. The alien megastructure idea was vulnerable to color-dependent dimming. Dust survived that test better. The exocomet picture was vulnerable to questions about where the comets came from. A giant perturber could help answer that. Now the giant companion idea is vulnerable to something even cleaner. Prediction? More radial velocity points should strengthen or destroy the wobble. Astrometry should reveal or reject the corresponding sideways motion. And another transit, appearing inside one of the allowed windows, would transform a lonely 2019 event into an orbit. That is the beauty of this stage of the mystery. For years, Tabby's star seemed strange because almost anything could be imagined around it. Now the possibilities may finally be becoming narrow enough to fail. And one of the next failures, or confirmations, could tell us whether the object behind the galaxy's strangest star is not a cloud, not a structure, and not one shattered comet, but a massive unseen world whose gravity has been shaping the entire system from the dark. The next question is where such a world could have come from, and whether its size makes sense around a star like this at all. That question leads directly into one of the messiest boundaries in astronomy. If the candidate around Tabby's star is real, what exactly is it? The best fit mass is about 9.4 times Jupiter's, but the uncertainty is wide. The same analysis gives it a radius of about 1.7 Jupiters and places it roughly 2.35 astronomical units from the star, a little more than twice the Earth-Sun distance. Its preferred orbital period is around 1,211 days, or about 3 1/3 years, although several narrow period windows remain possible. That combination puts the object in an uncomfortable category. Call it a planet, and it is an extreme one. Call it a brown dwarf, and it sits near the light end of that population. The famous dividing line is often placed near 13 Jupiter masses, where an object may become massive enough to fuse deuterium for a time. But nature does not place a painted stripe at 13. Formation history matters, and astronomers do not use one perfectly agreed boundary. The 2026 study itself treats the candidate as occupying the overlap between giant planets and brown dwarfs, rather than pretending the label is settled. You can understand the difference by imagining two very different births. A giant planet can begin inside a disk of gas and dust around a young star. Small material gathers. A solid core may grow. If conditions are right, that core pulls in a huge envelope of hydrogen and helium until a world like Jupiter emerges. A brown dwarf can form more like a star. A patch of a molecular cloud collapses under its own gravity. But the final object never becomes massive enough to sustain normal hydrogen fusion like the Sun. From the outside, those histories can produce objects with overlapping masses. So mass alone may not tell us how this one was born. And its radius adds another puzzle. At roughly 1.7 Jupiter radii, the candidate would be physically enormous. Yet giant planets and brown dwarfs do not keep getting wider as you pile on mass. Strong gravity compresses them. Over a broad range, adding more material can make an object much heavier without making it much larger. That is why Jupiter-sized bodies can hide radically different masses inside nearly similar silhouettes. The paper notes that the measured radius overlaps both giant planets and transiting brown dwarfs. So radius does not settle the identity either. But there is a twist hiding inside that measurement. The transit may not be showing us the naked body. During the 2019 event, TESS recorded a brightening centered near the transit. The feature does not appear the same way in the other observed sectors. If that brightening is astrophysical rather than instrumental or stellar noise, one possible explanation is forward scattering from dust around the companion. In simple terms, dust grains could bend some starlight toward us just before or around the time they also help block the star. Now picture what that would mean. You think you are measuring the edge of a giant world, but you may actually be measuring the edge of a dusty envelope around it. The solid or gaseous body could be smaller than the transit makes it look. That possibility is not confirmed. The paper explicitly says dust around the companion cannot be ruled out. It does not claim that such dust has been detected. But if future observations support it, the system becomes much more interesting, because the object suspected of disturbing dusty bodies might itself be wrapped in dust. And that brings us back to formation. A giant object at about 2.35 astronomical units is not sitting almost against its star like a hot Jupiter. Its fitted equilibrium temperature is only about 268 Kelvin under the assumptions used in the study. That is cold by hot Jupiter standards. And the authors note that its temperature is broadly consistent with other massive long-period planets. So this is not obviously a bloated furnace hugging the star. It is a cool, distant heavyweight. If it formed in a planetary disk, then at some point that disk managed to build or preserve an object with many Jupiter masses. If it formed more like a brown dwarf, then Tabby's star may have acquired something closer to a miniature stellar companion on a surprisingly compact orbit. Those histories would tell us very different things about the architecture we are looking at now. And architecture matters because the candidate is not alone. Far away, the known low-mass stellar companion already pulls on the system over enormous timescales. Closer in, the proposed giant could dominate the motion of smaller bodies near its orbit. You can imagine the system not as a star with one mysterious cloud, but as a hierarchy. Star, possible giant companion, smaller debris, then another star far beyond them. Each layer can exchange momentum. Each layer can reshape an orbit. Given enough time, quiet geometry can become violence. A planetesimal that misses the giant by a safe distance today may return on a slightly altered path. A resonance can keep repeating the same gravitational push. Its orbit stretches, its closest approach to the star falls inward. Eventually heat, tides, collisions, or all three can turn one solid body into many fragments. Then the fragments become dust. Then the dust becomes a dip. This chain is attractive because it connects the clean 2019 transit with the dirty Kepler dips without demanding that they be the same kind of event. The giant crosses as a giant. The debris crosses as debris. One system gives us both, but there is still a major missing piece. If the candidate really is the engine sending material inward, then the locations and timing of the old dips should contain some fingerprint of that orbital architecture. They may not repeat every 3 years like a planet. The fragments could take very different paths, yet their distribution should not be completely arbitrary if one massive perturber is doing much of the scattering. The authors tested how the Kepler dips line up when the old light curve is folded across the 5 remaining candidate periods. They stopped short of claiming a connection. A deeper analysis is still required. That restraint gives us the next real question. Not merely whether a giant companion exists, but whether its orbit can explain the timing of the star's most famous disappearances. Because if those two clocks can be connected, then the object hiding behind Tabby's star would become more than another planet candidate. It would become the first plausible piece of machinery behind the mystery itself. The old dips look chaotic, but chaos does not always mean randomness. Sometimes it means we have not found the clock yet. That distinction matters because the proposed companion gives us something Tabby's star has rarely offered: a possible orbital period. The 2026 analysis found that the smooth TESS transit from September 2019 can only fit a limited set of long-period orbits once earlier photometry is taken seriously. The companion, if real, must take at least about 1,030 days to circle the star, and only 5 narrow period windows survived the combined constraints. Now imagine taking the entire Kepler light curve, the famous years of irregular dimming, and laying it on top of itself every time one of those candidate periods passes. Astronomers call this folding a light curve. The phrase sounds abstract. The picture is not. Suppose you have a stack of transparent calendars. On each one, you mark every day the star faded. Then you slide the calendars until every possible orbit of the hidden companion begins on the same day. If the dips repeatedly cluster at a particular orbital phase, the marks begin to pile up. Suddenly, what looks scattered in ordinary time may reveal structure. If nothing lines up, the page stays messy. That is the test. And it is tempting because the companion hypothesis does not require every dust cloud to cross at exactly the same time. A massive perturber could disturb smaller bodies near certain parts of its orbit, while those bodies then take their own routes toward the star. The delay between gravitational kick and dusty transit could vary. Different fragments could need different numbers of orbits before they finally dive inward. So we should not expect a perfect row of identical eclipses. What we might expect is preference. Certain phases could be busier than others. Certain families of dips might be related. And if such a preference survives statistical testing, it would give us something far stronger than a visual resemblance. It would give us a dynamical connection. The researchers behind the 2026 paper did perform an initial phase folding exercise using the 5 remaining orbital windows, but they did not claim that the Kepler dips had been solved. Their conclusion was deliberately limited. The possible connection deserves a deeper analysis. That restraint is important because Tabby's star can fool you. There are many shapes. There are many ways to choose a period after looking at the data. With enough freedom, some events will appear to line up by accident. This is one of the oldest traps in pattern hunting. Human eyes are very good at finding shapes in noise, especially when we already know what we hope to see. 2 deep dips separated by nearly the same interval can feel like a clock. Add a third event that almost fits, and the story becomes seductive. But almost is dangerous. An orbital model has to survive all the places where a transit should have happened and did not. That is exactly why the old observing windows are so valuable. Kepler watched Tabby's star for years. TESS returned later. Ground-based surveys filled other pieces of time. Every stretch of clean coverage becomes a locked door. If a proposed period predicts that the giant companion should have crossed during one of those stretches, and no corresponding smooth transit exists, that period can be rejected. Absence becomes evidence. Not because nothing happened anywhere, but because a specific model promised that something should happen there. This is how the 5 surviving windows emerged. The team did not simply search for a period that looked attractive. They used the 2019 transit as an anchor and asked which repeated crossings could have escaped all the earlier observations. The result was a long-period companion with only restricted places left to hide in time. That changes how we should think about the old chaotic dips. They do not need to be direct transits of the giant. In fact, the strongest evidence says they probably are not. Multi-wavelength observations of Tabby's star have shown that the irregular dimming is consistent with dust, and the 2026 paper describes the leading explanation as dust from exocomets, or planetesimal fragments. The smooth TESS event, by contrast, is unusually symmetric and is poorly reproduced by the exocomet models tested in that study. So we may be looking at 2 different populations of events. One is the suspected perturber. The other is the material it may perturb. Think of a wrecking ball behind a wall. You might never see the ball itself, only clouds of plaster falling from different places. The debris does not copy the motion of the ball, it responds to it. That is the kind of relationship astronomers now have to TESS. If a giant object repeatedly stirs reservoirs of smaller bodies, computer simulations can ask how often those bodies are scattered inward, how long they take to reach star-grazing paths, and whether their arrival times resemble the actual Kepler dips. The models can change the companion's mass, eccentricity, inclination, and location. They can populate the system with thousands of test bodies and watch which ones survive, which ones escape, and which ones plunge toward the star. The result would not be a single pretty curve. It would be a probability map. And that is what this mystery needs. Because dust is messy by nature, a fragment can split into 10 pieces, one piece can outgas more strongly than another, a cloud can spread until it becomes almost transparent, several clouds can overlap and make one deep event. The same parent body can produce shadows that look completely different on separate passages. The model therefore has to reproduce behavior, not just one silhouette. There is also a more brutal possibility. The giant companion could be real and have nothing to do with the famous dips. Planetary systems can contain several unrelated phenomena at once. We could have a massive long-period object making the smooth 2019 transit, while an independent reservoir of dust produces the Kepler dimming. Finding one mysterious object does not automatically make it responsible for every other mystery nearby. That possibility is scientifically healthy. It forces the hypothesis to earn the connection. The companion must do more than exist. Its orbit must make sense. Its gravity must be strong enough. The debris must have somewhere to come from. The timing must not contradict the observations. And ideally, the model should predict something we have not yet seen. That last requirement is where the story becomes exciting, because the next decisive clue may already have a date attached to it. If one of the surviving orbital windows is correct, the hidden object is moving toward another geometrically meaningful moment. A future transit could repeat the smooth 2019 signature. New radial velocity measurements could trace more of the stellar wobble. Gaia astrometry could expose the sideways pull. Each result attacks the same object from a different direction. And if they converge, we may finally know whether Tabby's star has been hiding a giant companion all along. But even confirmation would leave one enormous question. If this object is the gravitational engine behind the dust, where is the reservoir it has been feeding from? Because a planet can scatter debris only if there is debris available to scatter. And somewhere around this star, there may be an entire unseen population of frozen and rocky bodies waiting in the dark. If the companion is the engine, then somewhere around Tabby's star there has to be fuel. Not fuel in the ordinary sense, a reservoir, a population of small bodies, icy, rocky, or both, large enough to survive for millions or billions of years, yet vulnerable enough that gravity can eventually knock some of them loose. Without that population, A massive planet can stir all it wants and still produce no dusty parade across our line of sight. The obvious analogy is our own solar system. Beyond Neptune lies the Kuiper Belt, a broad population of frozen bodies left over from planet formation. Far beyond that may be the much more distant Oort cloud, a vast reservoir whose objects can spend almost their entire existence in deep cold before a gravitational disturbance sends one inward. When that happens, an object that was nearly invisible can suddenly become active near the Sun, releasing gas and dust and growing a tail. We do not know that Tabby's star has anything arranged exactly like those structures, but the physics gives us a useful picture. A reservoir does not need to glow brightly all the time. In fact, one of the oldest constraints on Tabby's star is that astronomers have not seen the kind of strong infrared excess expected from a huge amount of warm dust. The discovery paper found no significant infrared excess, and later Spitzer observations also failed to reveal the bright heat signature that would be natural after something like a recent giant planetary collision. That absence once made the mystery harder. If dust is blocking so much starlight, where is all the thermal radiation from the dust? But the contradiction is not as simple as it sounds. Dust that crosses our line of sight does not have to form a thick shell around the entire star. A relatively narrow stream can block part of the stellar disk from our viewpoint, while intercepting only a small fraction of the star's total light in every direction. And if the parent bodies spend most of their time far from the star, on long, eccentric orbits, much of the reservoir can remain cold and faint until individual objects plunge inward. Models built around highly eccentric fragments have been attractive, partly because they can produce temporary dust without demanding a permanently brilliant warm debris disk. Now add a massive companion. A body near 9 Jupiter masses would not need to manufacture the reservoir. It would only need access to it. Imagine thousands of dark objects moving on neighbouring lanes around the star. Most never come close enough to interact strongly with the giant, but orbital resonances can act like repeated taps on a swing. Each gravitational encounter happens at roughly the right phase. The effect accumulates. A formerly modest orbit becomes more stretched until its closest approach dives toward the star. Then the body enters a new environment. Ice begins to escape. Rock heats. Cracks widen. Fragments separate. Radiation pressure grabs the smallest grains and pushes them away. A quiet object becomes a moving dust factory. This is one reason the dust around Tabby's star may have to be continuously renewed. Long-term multicolor monitoring found that the dimming is stronger at bluer wavelengths, consistent with small dust grains, including grains down to roughly 1/10 of a micron in some interpretations. Such tiny particles do not simply remain parked forever around a luminous F star. Radiation pressure can remove them quickly enough that fresh dust production becomes important. So the mystery may not be asking us to find one ancient cloud. It may be asking us to find a supply chain, reservoir, perturbation, destruction, dust, transit, loss, then repeat. That picture also explains why the system can look empty when we search for a giant debris disk. Submillimeter observations found no significant emission at the star and placed strong upper limits on the amount of dust in parts of the inner system. Those measurements made a catastrophic destruction event involving a large planet less attractive, while remaining compatible with much smaller amounts of transient material. In other words, the system does not appear to be drowning in dust. It may be leaking dust. That is a very different machine. Instead of smashing one enormous world and leaving a glowing cloud, gravity could feed smaller objects inward, one group at a time. Each episode would create enough material to dim the star from our particular viewing angle, then fade as the grains disperse. And the numbers do not require a whole planet to be pulverized every time. Early submillimeter work estimated that the dust needed for one major Kepler dimming episode could be extremely small on planetary scales, even though producing it might still require the destruction of many comet-sized bodies. The same study found that a cometary breakup picture could fit within the observational dust limits far more comfortably than a catastrophic planetary collision. This is where an unseen reservoir becomes powerful. You do not need one impossible object. You need many ordinary ones. The challenge is that we have not directly imaged such a belt around Tabby's star. The 2015 and 2016 observations constrained the amount of dust, but a population of large, cold parent bodies can be far harder to detect than the fine grains they occasionally produce. A kilometre-scale frozen body at hundreds of astronomical units is not a bright beacon. From more than 1,000 light-years away, an entire population could remain unresolved and nearly invisible. So astronomers have to look for consequences. One consequence is the dust itself. Another is orbital structure. A real belt being stirred by a massive companion should evolve differently from a random cloud placed around the star by hand. Numerical simulations can populate the system with thousands or millions of test particles and ask which orbital configurations deliver material toward the star. Change the giant's orbital eccentricity, and the delivery rate changes. Tilt its orbit, and different regions become unstable. Add the known distant stellar companion, and new secular effects can appear over much longer timescales. That is where this system becomes more than a transit mystery. It becomes celestial mechanics. The 2026 companion paper explicitly points to planetary perturbations as a possible way of supplying incoming exocometry material, but it does not demonstrate the full chain. The candidate itself remains tentative, and the reservoir remains inferred rather than observed. So there are still several ways for this picture to fail. The companion may vanish with better radial velocity data. It may be real but dynamically irrelevant to the dust. The dust reservoir may sit in a region the companion cannot efficiently disturb. Or the dips may come from a completely different mechanism. Yet the new idea has one enormous advantage over many older explanations. It can be attacked. We can measure the orbit. We can simulate the scattering. We can search for cold material. We can watch for new dips. And we can ask whether those dips appear when the dynamical model says fresh debris should be arriving. If those pieces begin to agree, then the darkness around Tabby's star will stop looking like a collection of unrelated shadows. It will start looking like an ecosystem. A massive, unseen companion would be the shepherd. A distant reservoir would be the herd. And every strange fade we see would be one small piece of that hidden architecture falling toward the light. But before we accept that picture, we have to confront something even stranger. Tabby's star does not only experience short, sharp dips. It has also appeared to change brightness over much longer stretches of time. And any explanation that hopes to solve the star must somehow survive both clocks. The star has more than one clock. For most people, Tabby's star became famous because of the dramatic Kepler dips, sudden losses of light lasting days, sometimes deep enough to remove roughly 1/5 of the star's brightness. But buried underneath those spectacular events was something slower. The baseline itself was moving. Using Kepler's full-frame images, Benjamin Monte and Joshua Simon found that KIC 8462852 faded gradually during the first roughly 1,000 days of the mission, losing about 0.9% of its brightness. Then the decline accelerated. Over roughly the next 200 days, the star dropped by more than another 2% before becoming comparatively stable near the end of the Kepler record. Among hundreds of comparison stars, nothing showed the same combination of behavior. That is not a comet flashing across the face of a star for an afternoon. That is the room getting darker while you are still standing inside it. And it creates a much harder problem. A compact dust cloud can explain a short dip if it happens to pass directly between us and the star. But a decline lasting months or years requires either a much larger structure, a sequence of overlapping structures, or a changing amount of material that keeps blocking some fraction of the light for a very long time. Then observers kept watching. From 2015 into 2016, measurements from Swift, ground-based telescopes, and Spitzer showed another slow fading episode. Crucially, the amount of fading changed with wavelength. The star dimmed more strongly at shorter wavelengths and less strongly in the infrared. That is the behavior expected when small particles are involved, because dust does not treat every color of light equally. So the slow darkness also had color. That matters because it points toward a possible connection between the long-term fading and the shorter dips. In both cases, a perfectly opaque solid screen is a poor fit. Dust remains the more natural language. Later monitoring from 2015 through 2018 made the picture even stranger. Observers recorded a continuing slow decline, with broad dimming structures lasting roughly 4 to 6 months, while the amplitudes again became smaller toward redder wavelengths. The researchers argued that the same dust extinction physics could span a continuum from short dips to much longer fading episodes. Imagine rain passing a streetlight. One drop crossing the beam gives you a blink. A thin sheet of rain gives you a longer fade. A storm stretching across the entire road changes the background brightness for minutes. The timescale changes, but the material does not have to. That is an attractive way to think about Tabby's star. Instead of inventing one mechanism for the day-long Kepler dips and another for the slow baseline changes, perhaps we are seeing dusty structures of different sizes, densities and orbital geometries. But this is where the story becomes dangerous if we make it too neat. There was also a famous claim that Tabby's star had been fading for nearly a century. Archival Harvard photographic plates were interpreted as showing a decline from the 1890s to the late 1980s. If that trend were fully secure, the amount of obscuring material required would push the dust problem onto an enormous scale. Other analyses challenged that result, arguing that systematic changes in the photographic plate archive could mimic at least part of the apparent century-long fading. So the century-scale behavior should not be treated with the same confidence as the fading measured directly during Kepler and modern CCD monitoring. That distinction helps us keep our feet on the ground. We know the star changed on year-scale baselines during Kepler. We know later monitoring found additional slow variability. We know much of that variability is chromatic in a way consistent with dust. What remains uncertain is how far backward in time the same behavior truly extends. Now place the proposed giant companion back into this picture. At first, the companion seems built for the wrong job. A planet or brown dwarf crossing the star should produce one clean transit, like the smooth event TESS recorded in 2019. It cannot simply sit in front of the star for years. Its orbit carries it away. But its gravity can act when the body itself is nowhere near our line of sight. This gives us a possible separation of roles. The giant companion produces the clean transit. Its gravitational influence helps rearrange smaller bodies. Those bodies produce dust. And the dust, depending on how it is distributed, can create shadows lasting hours, days, months, or perhaps longer. The key is geometry. A single compact fragment cloud gives a narrow feature. A long train of debris stretched around an orbit can cover the star repeatedly. Many clouds arriving close together can overlap until the light curve no longer returns to its previous baseline between events. From Earth, that overlapping debris can look like the star itself has slowly faded, even if the stellar surface has not changed at all. This is where the reservoir plus perturber idea becomes more ambitious. It no longer has to explain only why fresh dust exists. It has to explain why dust appears across radically different timescales. That is a much tougher test. The 2026 companion study does not claim to have passed it. The giant companion remains tentative, and the paper presents planetary perturbation as a possible source of the exocometry material rather than a completed dynamical solution. To turn that possibility into a real model, simulations would need to reproduce more than occasional inward scattered bodies. They would need to generate enough material with the right distribution to create both sharp events and broad periods of extinction while still respecting the system's infrared limits. And there is another pressure point. Small dust grains do not last forever near a luminous star. Radiation pressure can push them out of the system. That means a model invoking fine dust over long periods needs renewal. The darkness cannot simply be one static curtain that has been hanging there unchanged for decades. Something has to keep making the curtain. That is why a dynamic system is so appealing. The star may be surrounded not by one mysterious object, but by a process. Bodies are perturbed. Some move inward. Some break apart. Fresh grains spread into elongated streams. Radiation removes the smallest grains. Then another group arrives. From our distant viewpoint, the result is not a repeating planetary clock. It is a flickering, evolving screen whose thickness changes as the supply changes. And if that picture is correct, one strange prediction follows. The darkest moments may not be the most important ones. The quiet years between the famous dips could contain the fingerprints of the entire mechanism. Tiny color changes, slow baseline shifts, weak infrared variations, and subtle patterns in when new dust appears. Tabby's star may have been telling us what surrounds it even when it looked almost normal. The next challenge is therefore not simply to wait for another spectacular plunge. It is to separate what belongs to the star from what belongs to the material in front of it. Because before we can blame an unseen giant for creating the darkness, we must answer a more basic question. Could the star itself be responsible? It is an uncomfortable question. Because if the answer were yes, then much of the machinery we have been building around Tabby's star could become unnecessary. No giant cloud, no train of shattered comets, no hidden reservoir constantly feeding dust inward. Perhaps the star simply changes its own brightness in a way we do not yet understand. Stars do change. They pulse. They rotate. They grow spots. Their magnetic fields reorganize. Their surfaces boil with convection, and some stars brighten or fade because different regions rotate into view. If you watched our own sun from far away with a sufficiently precise instrument, its light would not be perfectly steady either. So, before blaming anything outside Tabby's star, astronomers had to ask whether an unusual F-type star could create these signals from within. At first glance, that idea has one attractive feature. It solves the energy problem. If the star is simply producing less visible light for a while, then we do not need a large amount of material positioned at exactly the right angle between us and the star. The fading would belong to the source itself. Several intrinsic ideas have therefore been explored over the years, including unusual magnetic activity, large surface structures, and models in which the star temporarily stores or redistributes energy beneath its surface. But the dips fight back. The first problem is their shape. Tabby's star does not merely drift gently up and down like a conventional variable star. Kepler saw abrupt, irregular structures with depths reaching roughly 20%. The original discovery team found the star to be an otherwise fairly normal main sequence F star and confirmed that the events were astrophysical rather than a detector or processing artifact. To dim an entire star internally by 20% over a short interval is not a small adjustment. That is like turning down 1/5 of a furnace and then restoring it without the clean pulsation pattern we normally use to recognize stellar variability. Still, strange does not mean impossible. So astronomers looked for another discriminator. Color. This is where the external material picture becomes much harder to escape. During later dimming events, observers measured the star simultaneously at different wavelengths. The dips were deeper in blue light than in red light. Ground-based spectrophotometry found a clear non-grey signature compatible with small, optically thin dust grains. The long-term fading shows the same general kind of clue. Swift, Spitzer, and ground-based observations from ultraviolet through infrared found that the amount of fading depended on wavelength. The pattern favoured circumstellar extinction rather than a simple, uniform loss of stellar luminosity. That word, extinction, is important. It does not mean the star is dying. It means light is being removed from our line of sight by material between the source and us. Imagine placing a very thin, smoky film over a white lamp. The lamp has not changed. But the smoke does not block every color equally. Depending on the grain sizes, blue light can be scattered or absorbed more efficiently than red light. Now remove the film. The lamp looks normal again. That is close to what the color information is telling us. And the same test becomes even more powerful when the timescale changes. Monitoring from 2015 through 2018 found broad fading structures lasting roughly months. Superimposed on a longer decline, those changes were again stronger in blue bands and weaker toward redder bands. The authors argued that ordinary dust extinction could connect short dips and much slower fading. So we have a strange convergence. A dip lasting days, says dust. A fade lasting months, says dust. A long-term brightness change also carries a dust-like color signature. That does not prove every event comes from exactly the same cloud population, but it means any purely intrinsic explanation has to reproduce something that looks remarkably similar to wavelength-dependent extinction across several different timescales. That is a high bar. There is also the temperature problem. If the entire stellar surface genuinely became much cooler during a major dimming, we might expect corresponding changes in the spectrum and color that follow stellar atmosphere behavior. Instead, the observed wavelength dependence in the well-measured dips has repeatedly been interpreted as intervening particulate material. And yet the star cannot be removed completely from the story. Why? Because real stars have noise, rotation, surface activity, pulsation, and instrumental systematics can all sit underneath circumstellar events. Even the radial velocity search for the possible giant companion has to contend with the fact that stellar behavior can imitate or distort the tiny wobble astronomers are trying to measure. This means the mystery is not a choice between a perfectly constant star and external dust. The real problem is separation. How much of the signal belongs to the star? How much belongs to material around it? And which parts, if any, belong to the proposed giant companion? Think of listening to someone through a wall during a storm. The voice is the star. The wall is the circumstellar environment. The rain is measurement noise. You cannot understand the sentence by assuming every sound comes from only one source. Astronomers separate those sources by making them disagree with one another. A surface feature rotates with the star. A pulsation carries characteristic frequencies. Dust produces wavelength-dependent extinction. A planet produces a repeatable gravitational pull. A transiting solid body produces a geometric shadow. Each mechanism leaves a different fingerprint. That is why the new 2019 TESS event is so interesting. It is not merely another disappearance. The 2026 analysis describes it as a unique, symmetric transit that is consistent with a planet or brown dwarf and distinct from the irregular dust-driven behavior that made Tabby's star famous. In one system, we may therefore be seeing the fingerprints of different components laid over one another. The star provides the light. Dust produces much of the chaotic dimming. A massive companion may produce the clean transit and possibly help create the dust. That is a far more complicated answer than saying, the star itself is variable. But complexity is acceptable if every extra piece can be tested. The dust can be tested with color. The companion can be tested with transit timing, radial velocity, and astrometry. The star can be tested with spectroscopy, rotation signatures, and long-term activity indicators. And every new observation can move light from one box into another. This is how the mystery is slowly becoming less mysterious. Not because one spectacular observation suddenly explains everything, because different hypotheses are being forced to leave different fingerprints. For the famous dips, external dust has survived that process unusually well. For the smooth 2019 event, dust alone now looks less comfortable. And for the long-term changes, the evidence again keeps pointing toward material somewhere between us and the stellar surface. So the star may not be creating the shadows. It may be illuminating an entire hidden environment. But if that environment really contains a massive companion, scattered debris, and recurring dust clouds, one question becomes unavoidable. Why are we able to see any of this? Planetary systems exist around countless stars. Debris exists around countless stars. Giant planets exist around countless stars. Yet almost none of them blink like Tabby's star. Something about our viewing angle may be extraordinarily special. Something about our position may be part of the mystery. If the possible companion really crossed Tabby's star in 2019, then its orbit is not pointed randomly across the sky. It has to pass almost exactly between us and the star. The system may be tilted in just the right way for a distant giant to sweep across the stellar disk from our viewpoint. That sounds ordinary, because most planets we hear about were found through transits. But transits are geometrically rare. The candidate's preferred orbit places it about 2.35 astronomical units from Tabby's star, farther out than Mars's from our Sun. At that distance, the star looks tiny from the companion. Using the fitted sizes and orbital distance, simple transit geometry gives a chance of only a few parts in 1,000 for a randomly oriented orbit to cross the stellar disk at all. Think of holding a coin several hundred steps away and trying to roll a marble through a line directly in front of it. Most paths miss. A transit means we are looking almost along the orbital plane. And if the same broad plane also contains smaller bodies, fragments, and dust, our viewing angle could help explain why this particular system looks so extreme to us. That last step is not established. A transiting giant does not prove that the dusty material shares its plane. Planetary systems can be warped. Comets can arrive on highly tilted orbits. The known distant M-dwarf companion could even help change those inclinations over long periods. So we cannot draw one flat disk around the star and declare the problem solved. But the geometry gives us something worth testing. The 2026 fit gives the candidate an impact parameter of about 0.76. That means the suspected object would not cross directly through the center of the star. It would trace a chord noticeably above or below the middle of the stellar disk, while still producing the smooth U-shaped event seen by TESS. That is a physical path. Now compare it with the dust. A dust cloud does not have to cover the entire star to create a deep dip. It only has to place enough grains across the small patch of sky occupied by the stellar disk. From more than 1,000 light-years away, that disk is an extraordinarily narrow target. So every famous dip carries a hidden statement about geometry. Some material was not merely present around Tabby's star. It crossed our exact line of sight. Again, and again, and again. That repetition is one reason families of related fragments have remained attractive. If many pieces share similar orbits after a breakup, one favorable orbital orientation can allow several members of the family to transit instead of winning the geometric lottery separately for every cloud. We may be watching many pieces moving along related paths. Picture a freight train crossing a distant road. You do not need every carriage to choose the same intersection independently. Put the rails across the road once, and every carriage follows. A family of fragments can work the same way. The bodies need not arrive at identical times or carry identical dust tails, but if their orbital planes and paths are similar enough, one viewing angle can expose a whole sequence of events. This is also why the new companion is potentially more important than one extra transit. If its orbit turns out to be aligned with the paths that feed the dusty material, it could reveal the hidden plane of the system. We would have a reference line around which to build dynamical models. If it is badly misaligned, that is information too. A tilted giant can stir a debris population differently from one embedded calmly inside the same disk. It can pump inclinations, increase eccentricities, and open routes that a flat, quiet system might never use. Then there is the distant stellar companion. It sits roughly 885 astronomical units away in projection. That is so far out that light itself takes several days to cross the separation. Yet over millions of years, a second star can still reshape orbits through repeated gravitational torques. Researchers have explored whether this wide companion could drive an eccentric Kozai lid-off process, gradually pushing planetesimals from a distant belt onto extreme star-grazing paths if the orbital planes are sufficiently misaligned. The mechanism is real. Its success here is uncertain. A 2023 modelling study found that the wide binary pathway can create the right kind of highly eccentric planetesimals under some conditions, but estimated that observing a Tabby-like event through that specific mechanism in the Kepler field would be unlikely. That is useful because it prevents the distant star from becoming a magic answer. It can influence the architecture. It does not automatically explain the dips. Now add the tentative inner giant, and the geometry becomes richer. The outer star may apply a slow torque. The inner heavyweight may scatter smaller bodies more directly. A reservoir may supply the material, and our line of sight may cut through exactly the region where the consequences become visible. None of those links is guaranteed, but together they suggest a different way to understand why Tabby's star appears unique. Perhaps its physics is not unique. Perhaps our view is: many planetary systems may contain cold belts, giant planets, distant stellar companions, collisions, and inward scattered comets. Most of those events happen above, below, or beside the tiny disk of the host star as seen from Earth. Their dust never crosses the beam we happen to receive. Nothing dramatic appears in the light curve. Turn the same system sideways, and suddenly every inward moving stream has a better chance of cutting across the star. A quiet system becomes a dipper. This selection effect matters whenever we call Tabby's star strange. Kepler watched a huge stellar sample with extraordinary precision. Yet occulting material only becomes obvious when that material moves through our line of sight. We are not looking at a complete census of violent planetary systems. We are looking at the ones whose shadows happen to point at us. And Tabby's star may occupy the extreme tail of that alignment. The clean 2019 event makes that idea more concrete. If the event truly belongs to a giant companion on a multi-year orbit, then at least one major component of the system is already aligned closely enough to transit. The interpretation remains tentative, because the companion has not yet been confirmed. That is not proof that the dust shares the geometry, but it makes the question unavoidable. If the giant, the debris, and our line of sight are connected, then the next transit will not only tell us that the companion exists, its exact shape and timing can help pin down the orbital plane. Future dust dips can then be compared against that architecture rather than treated as isolated shadows. For the first time, we may be able to ask where the darkness sits in 3 dimensions. And that leads to an even larger question. If geometry is part of the reason Tabby's star looks so extraordinary, how many other stars are hiding similar systems simply because we are viewing them from the wrong angle? If geometry is part of the answer, then Tabby's star may not be unique in the way it first seemed. For years, this object was treated as the star that broke the rules, the one with dips too deep, too irregular, and too difficult to explain with an ordinary transiting planet. Kepler saw brightness losses reaching roughly 20%, with episodes lasting from days to many weeks, and the discovery team concluded that the events were astrophysical rather than instrumental. Their leading natural picture involved fragments from a disrupted family of exocomets or planetesimals, but rare and unique and not the same thing. If the phenomenon depends on a narrow viewing angle, then there could be many systems with similar debris dynamics that never announce themselves to us. Their comets may still break apart, their planets may still scatter smaller bodies, their dust may still cross the inner system. We simply do not see those clouds move directly across the stellar disk. This is one of the strangest biases in transit astronomy. We discover a system not only because of what exists there, but because of how the architecture is turned toward us. Imagine a thin sheet of paper held edge-on. You barely see it. Rotate it 90 degrees and suddenly it fills your view. Dusty planetary systems can work in the opposite visual sense. If the debris plane is close to face-on, material can orbit everywhere around the star without repeatedly covering much of the stellar surface from our perspective. Tilt the system toward edge-on, and the same structures gain a much better chance of crossing the beam. That can turn ordinary debris into extraordinary photometry. And astronomers have in fact searched for other stars whose light curves resemble pieces of Tabby's behaviour. One survey of candidate analogues reported 15 additional slow dippers, stars showing infrequent fading events rather than the clean periodic transits of normal planets. The sample did not prove that these objects share one mechanism with KIC 8462852, but it showed that low-rate dipping behaviour is not confined to a single point in the sky. An analogue does not need to be a perfect twin. If another star dims by only a few percent, or does so once every several years, it may still belong to the same broad physical family. The difference could come from how much dust is produced, how large the parent bodies are, how closely the system is aligned with us, or where we happen to catch it in its evolution. Tabby's star could simply be the extreme member we noticed first. There are other systems where exocomets themselves have become observable around Beta Pictoris. TESS detected asymmetric dips consistent with evaporating cometary bodies carrying extended dusty tails. Later analyses identified many more exocomet transits in that same planetary system. These events are not identical to the huge Kepler dips of Tabby's star, and that difference is important, but they demonstrate something fundamental. Small bodies outside our solar system really can produce detectable shadows when their dusty material crosses a star, so the basic ingredients are not exotic. Comets exist elsewhere. Dusty debris exists elsewhere. Giant planets exist elsewhere. Wide stellar companions exist elsewhere. What may be unusual at Tabby's star is the combination. Suppose a distant companion slowly changes the structure of an outer reservoir. Suppose a much closer giant object then scatters some bodies inward. Suppose those bodies fragment or evaporate. Then suppose our line of sight lies close enough to the active plane that the debris repeatedly crosses the star. Stack them together, and the result can look shocking. This is why the tentative 2019 companion matters beyond one planet candidate. The new study describes a smooth, symmetric TESS event unlike the irregular Kepler dips and finds tentative radial velocity support for a companion with a period of at least about 1030 days. The preferred mass is about 9.4 Jupiter masses, but the authors emphasize that the signal is only at roughly 2.3 sigma and still requires confirmation. If that object disappears under better data, the architecture changes. If it survives, the architecture gains a massive anchor. Then we can compare Tabby's star with other dipping systems in a more useful way. Instead of asking only, do their light curves look similar, we can ask, do they share the same machinery? Do they have massive outer planets? Do they have distant stellar companions? Do they show cold debris reservoirs? Are their systems viewed close to edge-on? Do their dips become deeper at bluer wavelengths, as dust predicts? Those questions turn a famous curiosity into a population problem. And population problems are powerful because they expose what one star cannot. With one object, almost any rare history can sound plausible. Maybe one enormous body broke apart at exactly the right time. Maybe one unusual collision happened just before Kepler looked. Maybe one distant companion happened to disturb one reservoir. Find 10 systems with the same architecture, and coincidence becomes harder to defend. Find 100, and statistics begins to tell us which ingredients actually matter. Tabby's star may also represent a short-lived phase. If the dramatic dipping requires a large body to fragment and spread dust for only a limited period, then most systems capable of producing the phenomenon would look normal for almost all of their lives. We would have to observe them during the brief interval when the debris happens to be dense enough and correctly aligned. That would make the star rare for 2 reasons at once. The geometry has to be right, and the timing has to be right. Imagine arriving at a highway after an accident. For hours before the crash, the road looks ordinary. Days later, the debris has been cleared. Only during a narrow window do you see the wreckage spread across the lanes. Kepler may have caught Tabby's star during the astronomical equivalent of that window. Or perhaps the process is not one accident at all. If a giant companion continuously feeds bodies from a reservoir onto destructive orbits, then the active phase could last much longer. Individual dust clouds would come and go, but the system could remain capable of producing new dips for centuries or more. Those two possibilities make different predictions. A single breakup should eventually run out of fragments. A continuously replenished system can keep producing new events. That means time itself becomes an experiment. Tabby's star has now been watched across multiple observing generations. The famous Kepler sequence was followed by new ground-based dips in 2017, demonstrating that the behavior did not simply end with the Kepler mission. Those later events were shallower, generally at the percent level, but they showed that fresh occultations were still occurring years later. So the system is still testable, and that makes the next decade unusually important. If the giant companion hypothesis is right, we should eventually recover its orbit. If the dust supply picture is right, new fading events should continue to reveal the properties of the grains, and possibly the dynamics feeding them. If analog searches grow, we may learn whether Tabby's star is a freak or the brightest warning sign of a hidden class of planetary systems. The mystery is therefore expanding even as one part of it narrows. We began with one star doing something impossible looking. Now we may be looking at a natural process that becomes spectacular only when mass, debris, timing, and geometry line up. But one old idea still hangs over every discussion of this object. Because before dust became the leading explanation, Tabby's star became famous for something far more dramatic. The possibility that the shadows were artificial. And to understand why that idea faded, we have to ask what an alien megastructure would actually do to the light. The alien idea did not begin because astronomers wanted aliens. It began because the light curve refused to behave like anything familiar. When KIC 8462852 first drew attention, the dips were deep, irregular, and aperiodic. Some remove roughly 20% of the star's light, and the events could last from several days to many weeks. The discovery paper tested a long list of natural explanations and found problems with nearly all of them, although a family of comet or planetesimal fragments remained the most consistent natural scenario available at the time. That awkward situation opened a door. In 2015, researchers discussing the signatures of large extraterrestrial engineering projects pointed out that a swarm of artificial structures crossing a star could, in principle, produce strange transit shapes that ordinary planets could not. Boyajian's star was identified as an especially interesting SETI target because its light curve looked compatible with the broad class of signals such structures might create. That statement was never the same as saying aliens had been discovered. It was a testable suggestion, and that difference matters. Imagine an advanced civilization placing enormous collectors around its star. You do not need one solid shell enclosing the entire sun. A swarm of separate structures could orbit at different distances and orientations. From far away, some could cross the stellar disk while others remained invisible. The resulting shadows might be deep, asymmetric, and non-periodic. On a Kepler light curve, that can sound uncomfortably similar to the original mystery. This is why the idea spread so quickly. It was visual. It was understandable. And unlike a normal planet, an artificial structure did not have to be round. But once you turn a spectacular idea into a scientific hypothesis, it inherits a problem. It has to survive new data. The first major pressure came from color. If a perfectly opaque structure crosses a star, it should remove nearly the same fraction of visible light at different wavelengths. Aside from smaller effects related to the star's surface and the structure's properties, dust behaves differently. Small grains scatter and absorb shorter wavelengths more efficiently. When Tabby's star dipped again after the Kepler mission, astronomers measured those events in multiple colors. The dips were deeper in blue light than in red. Ground-based spectrophotometry found a clear wavelength dependence compatible with optically thin dust containing very small grains. Later, multiband monitoring also found that several 2017 dips changed depth with wavelength rather than behaving like simple grey occultations. That is a serious clue. A giant opaque panel does not naturally look like smoke. Dust does, and the same color behavior appears not only in some short dips but in slower changes in brightness. That is one reason circumstellar dust moved toward the center of the explanation. Then comes the infrared question. A civilization collecting a substantial fraction of a star's energy cannot simply make that energy disappear. Any ordinary structure absorbing starlight should eventually re-radiate energy as heat, unless it uses some extremely unusual method to dispose of it. That heat could create an infrared signature. This is the basic logic behind searching for Dyson-like technology. Hide the visible star, and the energy may reappear at longer wavelengths. But observations of Tabby's star did not reveal the enormous warm infrared excess that a simple, heavily absorbing megastructure picture might lead us to expect. Early Spitzer measurements found no significant excess at 3.6 microns, and only a small, statistically insignificant signal at 4.5 microns. Those limits also created problems for natural ideas involving a recent catastrophic collision or a huge population of warm, dusty bodies. The absence of infrared excess did not mathematically eliminate every conceivable engineered structure. That is important. Mirrors can reflect rather than absorb. Structures could radiate at temperatures outside a particular observing band. A sufficiently creative civilization can always be given another engineering choice. But notice what happens when a hypothesis requires that move repeatedly. The explanation becomes harder to falsify. Science becomes strongest when a model makes predictions that could kill it. Dust made those predictions. It should alter colors. It did. Small grains should behave differently from solid, opaque screens. They did. A carefully arranged artificial system can be modified to imitate almost anything, but each extra freedom makes it less useful as the first explanation. Astronomers also searched for a different kind of evidence. Signal. The Allen Telescope Array observed the direction of KIC 8462852 across radio frequencies from 1 to 10 GHz and found no convincing narrowband or medium-band signals at the sensitivities of that search. Optical SETI observations also found no short, periodic, laser-like pulses above their detection thresholds. Later breakthrough listen work searched high-resolution optical spectra for powerful laser emission and again reported no compelling candidate. None of those null results proves that nobody lives there. They prove something narrower. Specific kinds of detectable technology were not found during those observations. A civilization might not transmit toward us. It might use frequencies we did not observe. It might not use obvious beacons at all. SETI searches are never a universal detector for intelligence. So the megastructure idea was not defeated because a radio telescope listened once and heard silence. It weakened because the natural evidence improved. The color dependence looked like dust. The infrared constraints could be accommodated by dust on suitable orbits. Real exocomets were discovered producing transit signatures around other stars. And now, in 2026, a tentative massive companion offers a possible physical way to keep feeding smaller bodies onto destructive paths. The new analysis finds a unique symmetric TESS event consistent with a giant planet or brown dwarf and tentative radial velocity evidence for a companion, while explicitly noting that more observations are required. That is a crucial shift. In 2015, one of the most frustrating questions was not merely what was blocking the star, but why so much irregular occulting material should exist there at all. A gravitational perturber gives us a mechanism to investigate. Not a completed solution. A mechanism. If that companion is confirmed, and simulations show that it can scatter a reservoir of planetesimals inward at the required rate, then a piece of the mystery that once invited exotic engineering may be explained by an unseen world obeying ordinary gravity. That does not make the old SETI work foolish. The opposite. Tabby's star became a useful example of how technosignature science should work. An observation appears that is difficult to explain. Artificial possibilities are allowed into the hypothesis space. Searches are designed. Natural explanations are tested at the same time. Then evidence changes the ranking. Aliens are not forbidden. They simply do not get a shortcut. And right now, dust is winning. But the lesson of Tabby's star is not that strange observations always become boring. The emerging natural picture may be more violent than the megastructure story ever was. Because if a giant unseen companion really is driving bodies toward the star, then somewhere in this system, entire worlds or comet-like objects may be having their orbits ripped apart, heated, fractured, and scattered into clouds large enough for us to see across more than 1,000 light-years. No engineering is required. Only gravity, time, and destruction. And the next step is to ask whether that destruction can actually produce the astonishing 20% shadows that started this entire story. The number that made Tabby's star famous is 20%. A star losing 1/5 of its light in a single irregular event sounds so extreme that the instinctive reaction is to imagine something enormous crossing in front of it. If the blocker were one perfectly opaque circular object, covering 20% of the stellar disk would require a projected radius almost 45% as large as the star itself. That would be enormous. But dust changes the geometry completely. A dusty cloud does not have to be one solid object. It can spread across a huge projected area while containing surprisingly little total mass. Each grain blocks or scatters only a tiny amount of light, but billions upon billions of grains acting together can turn a transparent-looking stream into a substantial shadow. This is why depth alone does not tell us the mass of the occulting material. The discovery analysis of KIC 8462852 estimated that the fragments associated with the events required a minimum total mass greater than about 1/1,000,000th of Earth's mass, corresponding to an original rocky body more than roughly 100 kilometers across. That is not trivial, but it is nowhere close to destroying a planet. Now translate that into something physical. A body 100 kilometers across would still be tiny beside Earth. Break it apart, grind some of the fragments into fine dust, stretch that dust along an orbit, then place the stream exactly between us and the star. You can create an enormous shadow without needing an enormous solid wall. The difficulty is concentration. A normal isolated comet does not appear able to do the job by itself. One modelling study found that a solar system-like comet would typically create a transit only around 1/10 of 1% deep and lasting less than a day. To approach the deepest 20% event, the authors needed a tightly grouped swarm, roughly 30 comets if each were about 100 kilometers in radius, or roughly 300 if each were closer to 10 kilometers. Their full model required many such bodies to reproduce the collection of dip. That sounds excessive. And it is supposed to. The point of the model was not that 30 giant comets definitely crossed Tabby's star. It was to ask whether ordinary material could, in principle, generate a shadow this extreme. The answer was yes, but only if the system had a way to concentrate a remarkable amount of debris. And that brings us straight back to the hidden companion. A massive planet or brown dwarf would not need to create dust grain by grain. Its useful role would come earlier in the chain. It could rearrange the orbits of large parent bodies, potentially causing groups of them to enter similar star-grazing trajectories. The 2026 companion paper specifically raises planetary perturbations as a possible way of supplying the incoming exocometry material, while stressing that the candidate companion itself still requires confirmation. So instead of imagining one impossible cloud appearing from nowhere, picture an assembly line. A reservoir contains large bodies. Gravity destabilizes some of them. A group moves inward. Heat, tides, collisions, or previous fragmentation release dust. The fragments spread. Then, for a few days, our line of sight cuts through the densest part of the stream. The star appears to collapse in brightness. The stream moves on, and the star returns. There is a second reason dust can produce deceptive shadows. Bias is not all or nothing. A cloud can be optically thin, meaning some photons pass through it. Different parts of the cloud can have different densities. The leading edge may be almost transparent. The center may be thick. The tail may fade gradually into empty space. When such a cloud crosses a star, you do not get the clean, flat-bottomed transit of a hard disk. You get structure, slopes, shoulders, multiple minima, a dip inside another dip. That is much closer to what Kepler actually saw. The deepest events were not repeated copies of one another. They had changing shapes and no simple periodic clock. The original Kepler study described irregular, aperiodic dipping activity lasting from roughly 5 to 80 days and concluded that a family of exocomet or planetesimal fragments was the most consistent of the natural scenarios considered at the time. But solving the optical depth creates another problem. Dust that catches starlight should also absorb energy and re-radiate some of it in the infrared. If you need enough dust to hide 20% of the star, why does Tabby's star not glow like an obvious warm debris disk? This has been one of the hardest constraints on every circumstellar model. The answer may again be geometry and timing. A dusty stream crossing our line of sight can block a large fraction of the tiny stellar disk from our perspective without intercepting 20% of all the light the star emits into space. Those are completely different fractions. Imagine holding a grain of sand directly in front of your eye. It can hide the moon. It does not absorb a meaningful fraction of the moon's total light. The same geometric principle operates here, only on astronomical scales. Models of material distributed around highly elliptical orbits have shown that the observed dips and longer dimming can be made compatible with infrared limits for suitable orbital distances and dust distributions in those models. Much of the material can spend its time far from the star, remaining relatively cold, then sweep through the hotter inner system around periastron. That makes the timing of infrared observations crucial. The short-lived dust concentration can produce a dramatic optical event without leaving a permanent infrared beacon. There is still no free lunch. Very small grains are vulnerable to radiation pressure from an F-type star. Modern color measurements imply particles reaching down towards sub-micron sizes, and observations of the longer fading have been interpreted as requiring continual or recent replenishment because the smallest grains can be removed rapidly. So the cloud cannot simply sit there forever. Something has to keep rebuilding it. That requirement is not a weakness unique to the companion hypothesis. It is the central physical demand of almost every dust explanation for Tabby's star. Where does the fresh material come from? How frequently is it produced? How do enough fragments enter our line of sight? And can the process continue without generating more infrared emission than we observe? Those questions are where the new candidate either becomes important or irrelevant. If future observations confirm a roughly giant planet to brown dwarf mass object, and dynamical simulations show that its orbit can repeatedly feed bodies into destructive trajectories, then the companion would solve one of the hardest missing steps. It would not explain the shadow by being the shadow. It would explain why the shadows keep being manufactured. That is a more subtle role, and a more powerful one. But 20% remains an extreme test. Any successful model must reproduce not merely enough dust, but the changing morphology, color dependence, duration, lack of simple periodicity, long-term dimming, and weak infrared signature all at once. This is why Tabby's star is still strange after a decade of study. We have ingredients that work individually. Dust can block the light. Fragments can make dust. Gravity can scatter fragments. A massive companion may provide that gravity. What we do not yet have is a single demonstrated chain connecting every link. And there is one way to make that chain much stronger. Catch the system while it is doing it again, and measure everything at the same time. The next deep dip should not merely be photographed. It should be dissected. The next decisive observation may already have a date. If the smooth TESS event in 2019 was a real transit, the hidden object must cross again. It cannot stay mysterious forever. An orbit is a promise. After enough time, the the same geometry returns, and the remaining windows are now narrow enough to watch. After comparing the 2019 event with Kepler, TESS, ground-based surveys, and follow-up observations, the 2026 team reduced the possible orbital periods to 5 small ranges. The first two, near 1030 and 1035 days, were partly tested in April and May 2025. No clean repeat transit appeared in the observed portions, although gaps prevented those windows from being erased completely. 3 later possibilities remain especially important: roughly October 18 to 23, 2026, January 15 to 16, 2027, and February 28 to March 2, 2027. That turns the mystery into a stakeout. You do not point one telescope at the star and hope. You build a net. Small ground-based telescopes can watch the brightness continuously from different longitudes, handing the target from one night to the next as Earth turns. A dip that lasts about 21 hours is longer than a single night at most observatories, so geographic coverage matters. One site can lose the star to daylight, while another site farther west takes over. The goal is simple. Do not miss the shadow. If a future event arrives with roughly the same depth, duration, and smooth U-shaped profile as the 2019 transit, the companion case becomes much stronger. The period would suddenly stop being a set of possible windows and become a measured clock. We would know how long the object takes to orbit. That would sharpen estimates of its distance from the star and allow every radial velocity measurement to be placed at a known point in the orbit. The 2026 paper explicitly states that detecting a future transit could confirm or refute the proposed picture. But brightness alone is not enough. During the next event, color becomes a weapon. If the blocker is a solid giant planet or brown dwarf, the central transit should be much closer to a geometric shadow than the famous dusty dips. If a dusty envelope surrounds the companion, however, the transit may change slightly with wavelength, and light scattered by those grains could create extra structure around the event. That possibility comes directly from something odd in the TESS data. The 2019 transit contains a brightening near its center. The same feature was not obvious in the other TESS sectors. The researchers suggest that, if the brightening is real and astrophysical, forward scattering by dust around the companion is one possible explanation. Dust could also make the transiting object appear larger than its physical body really is. So imagine the next transit recorded in several colors at once. Visible light falls. Near-infrared light falls. Spectra are taken before, during, and after the event. If every band follows nearly the same clean geometry, we learn one thing. If blue light changes more strongly, or if extra absorption appears in particular spectral lines, we learn another. The shadow becomes a probe of whatever surrounds the hidden object. At the same time, spectrographs can watch the star itself move. This is harder than it sounds, because Tabby's star spins rapidly, its spectral lines are broadened, making precise radial velocity measurements much noisier than they would be for a quiet, slowly rotating star. The 2026 study combined measurements from several instruments and still obtained only a tentative 2.3 sigma mass signal. That is why more radial velocity data matter so much. A real companion should pull the star in a repeatable way, not randomly, not only during a transit, across the entire orbit. If new velocity measurements rise and fall where the orbital model predicts, the gravitational case strengthens. If they flatten out or move in the wrong direction, the proposed companion can collapse even if the 2019 shadow remains unexplained. That is exactly what a useful hypothesis should risk. Then comes Gaia. The companion paper predicts an astrometric wobble of roughly 50 microarcseconds for its preferred solution. That angle is absurdly small. A microarcsecond is 1/1,000,000th of an arcsecond. Yet Gaia was designed to turn movements on that scale into measurements across years of repeated scanning. And the timing is remarkable. As of August 2026, Gaia Data Release 4 is planned for December 2, 2026. ESA says that release will be based on 66 months of observations. The Tabby star study argues that DR4 astrometry should be capable of testing a companion with the proposed characteristics. So within the same broad period when astronomers can watch some of the remaining transit windows, another completely independent test is approaching. One method watches the star dim. One watches its spectrum shift. One watches its position bend across the sky. 3 different effects. One hidden mass. That is the kind of convergence astronomers want. Because no single strange light curve has to carry the entire claim anymore. And if the object is confirmed, larger telescopes can ask a new question. What is it physically? The 2026 paper notes that future Hubble and James Webb observations could help study the companion and its atmosphere, particularly once another transit reveals the orbital timing more securely. That would be an extraordinary reversal. Tabby's star began as a mystery about missing light. The solution might eventually let us study the atmosphere of the object responsible for one of those shadows. But there is an even more important experiment hidden inside the next deep, dusty dip. When the star begins fading irregularly again, astronomers can measure the dust while the event is happening. They can track how the depth changes from blue to infrared. They can look for gas associated with evaporating bodies. They can measure whether absorption features accelerate across the stellar spectrum. They can check whether the timing matches any dynamical prediction tied to the giant companion. Then we are no longer asking whether dust exists. We are asking where it is moving. That is the transition this mystery needs. From composition to dynamics. From what blocks the light to what put it there. If a future transit confirms the giant and a future dust event shows material arriving on orbits that its gravity can plausibly create, 2 pieces that have spent a decade apart begin to connect. The clean shadow identifies the perturber. The dirty shadows reveal the debris, and the motion between them becomes the story. But there is one possible outcome we should not hide. The next windows may come and go with nothing. Gaia may show no compatible wobble. More radial velocities may dissolve the 2.3 sigma signal. If that happens, the 2019 event does not disappear from the data. It simply becomes mysterious again. Science does not owe us a neat ending. But Tabby's star is finally reaching the point where one of its biggest new ideas can fail in public. And that is progress. Because once the companion either survives or dies, we can ask the question that matters most. After more than a decade of strange shadows, what explanation is actually left standing? After more than a decade, the mystery is no longer empty. That may be the biggest change of all. When Tabby's star first became famous, the problem felt almost backwards. Astronomers had an astonishing light curve and too many possible stories. Comets, collisions, interstellar material, intrinsic stellar behavior, giant rings, artificial structures, dust clouds. Every explanation could solve one part of the problem, but almost none could solve all of it without creating another difficulty somewhere else. Now the evidence has begun to separate those stories. The irregular dips are not behaving like one opaque object. They are chromatic. They change more strongly in blue light than in red. That pushes us towards small particles. The long-term fading also carries a wavelength dependence consistent with extinction. That again pushes us toward dust. The lack of a huge, persistent infrared excess argues against some versions of a recent catastrophic collision and against a simple picture in which enormous amounts of warm material surround the star at all times. So the broad outline is sharpened. Something dusty is crossing our line of sight. But that is only the first layer. Dust tells us what the shadow is made of. It does not tell us why the shadow exists. And that is where the 2019 TESS event becomes so important. The smooth event looks different from the famous Kepler dips. Instead of a ragged cloud, it resembles the transit of one large body. The 2026 analysis found that exocomet-style models struggles to reproduce that shape, while a giant planet or brown dwarf-sized companion produced a cleaner fit. The same study then found tentative radial velocity evidence consistent with such a massive object on a long orbit. Not proof, a clue, but a clue that attacks the missing step. For years, the dust models needed a delivery mechanism. Something had to keep sending large bodies onto dangerous paths, or keep breaking them apart, or keep refreshing grains that stellar radiation would otherwise remove. A massive companion gives us a physically familiar way to do that. Gravity, no new physics, no invisible wall, no engineered structure, just an object heavy enough to reshape the orbits of smaller bodies over time. That does not mean the current picture is one giant planet orbiting peacefully while a few comets wander past. The emerging system is potentially much more complicated. There is the F-type primary star. There is the known distant stellar companion, hundreds of astronomical units away. There may be a much closer giant companion on a multi-year orbit. There may be one or more reservoirs of planetesimals. There are dust clouds crossing our line of sight. And there may be multiple dynamical pathways connecting those components. If that architecture is real, Tabby's star stops looking like a star with one bizarre obstruction. It becomes a planetary system in motion. Imagine the scene from outside. Far away, a faint second star drifts around on an enormous orbit. Closer in, a massive dark world moves around the primary every few years. Beyond or around it, frozen and rocky bodies occupy quieter paths. Most remain invisible. Then gravity begins to work. A resonance stretches an orbit. A distant stellar torque slowly changes an inclination. A close encounter with a giant companion scatters a smaller body inward. The body drops toward the star. Heat rises. Ice escapes. Fragments separate. Dust spreads. Then, because we happen to be viewing the system from a favorable angle, that debris crosses the stellar disk. From Earth, the entire dynamical history collapses into one thing. The star gets darker. This is why the proposed companion would matter even if its own transit is only 1% deep. It may be the least dramatic shadow and the most important object. The 20% dips catch your eye. The 1% transit may explain why the 20% dips exist. That reversal is exactly the kind of thing astronomy does well. The most spectacular signal is not always the deepest clue. But several rival explanations still deserve a place on the board. Intrinsic stellar variability has not been erased from every aspect of the light curve. Real stars are complicated. And some low-level variations can belong to the star itself. What has weakened is the idea that intrinsic behavior alone explains the major chromatic dips. A single catastrophic collision also remains physically possible in the abstract, but it has struggled with the lack of strong infrared emission and with the need to explain repeated activity over years. A one-time breakup of a large object can produce many fragments and may explain families of dips. The harder question is whether one breakup can sustain the observed behavior for long enough, or whether the system requires repeated replenishment. Exocomets remain highly relevant, but exocomets is not yet a complete mechanism. We still need to explain how enough of them arrive on the right paths. The alien megastructure idea remains logically imaginable, but it has lost the competition for explanatory efficiency. Once the dips showed dust-like color behavior and natural dynamical pathways became more plausible, artificial structures stopped being the simplest reading of the data. That does not make the story less extraordinary. It makes it physical. And physical stories give us leverage. If the giant companion is real, its orbit can be measured. If it perturbs debris, simulations can calculate the scattering rate. If the dust comes from specific parent bodies, spectroscopy may reveal gas released during their destruction. If the system is viewed nearly edge-on, future transit geometry should help reconstruct its architecture. Every piece can be attacked separately. That is what a mature explanation looks like. Not one sentence that magically solves everything, a network of claims, each vulnerable to a different observation. The weakest link right now is obvious. The giant companion itself, the 2019 transit, is still a single event. The radial velocity signal remains tentative. The orbit is not uniquely measured. And the connection between that object and the dusty dips has not been demonstrated dynamically. So we should resist the most tempting headline version of the story. We cannot yet say, astronomers found the object causing Tabby's star to dim. That would jump over several missing steps. A more accurate statement is more interesting. Astronomers may have found a massive object that could provide the gravitational architecture needed to help explain why dusty material keeps appearing around the star. That is not a final answer. It is a bridge between two previously separate mysteries. One mystery was the shadow. The other was the source of the shadow. Now they may belong to the same system, and if the next observations confirm that connection, the decade-long story of Tabby's star will end in a very different place from where it began. We started with a star whose light curve was strange enough to make people wonder about alien engineering. We may end with a system where ordinary gravity is quietly throwing smaller worlds toward destruction. There is something almost more unsettling about that. No intelligence is required. No one built the darkness. The system may be producing it naturally, again and again, and that leaves us with one final journey. Not into another hypothesis, but into the future. What would it actually take to say, with confidence, that the galaxy's strangest star is finally understood? To say that Tabby's star is understood, we would need more than one beautiful explanation. We would need the pieces to agree. First, the smooth 2019 event would have to become an orbit. A second transit, appearing in one of the allowed windows, with a similar duration and shape, would immediately change the status of the candidate companion. One lonely event would become a repeating object. The orbital period would stop being a range of possibilities and become a measured number. Then the star's motion would have to cooperate. Radial velocity measurements should trace the gravitational pull expected from that orbit. Gaia astrometry should reveal a compatible sideways wobble if the companion is massive enough and the geometry is favorable. If those independent techniques point toward the same mass and period, the hidden object would no longer be an attractive interpretation of one transit. It would be a real member of the system, but that still would not solve Tabby's star. Confirmation of the companion would answer only one question: what made the clean 2019 shadow? The larger mystery is why the star has produced so many irregular, dusty shadows over the years. That requires the next link. Dynamical simulations would need to show that a companion with the measured mass and orbit can actually disturb a plausible reservoir of smaller bodies, not once in an artificial computer setup, but at a rate and in a geometry that resembles what we observe. The model has to deliver material inward. It has to do it often enough, and it has to do it without destroying the rest of the architecture too quickly. Then the debris itself has to behave correctly. As bodies approach the star, models of heating, fragmentation, sublimation, and dust production must generate clouds capable of creating the observed depths and durations. Those clouds must contain grains that reproduce the wavelength dependence of the real dips. They must spread and disappear on timescales compatible with radiation pressure and orbital motion. And they must do all of this without creating more infrared radiation than telescopes actually see. That is a brutal test. It should be. A good explanation does not merely survive one observation. It survives collisions between observations. The optical light curve says one thing, the colors say another. Infrared limits impose another constraint. Spectroscopy adds another. Dynamics adds another. The system only becomes solved when one physical architecture can pass all of them at once. Then we would want prediction. This may be the most important step of all. Suppose a simulation using the confirmed companion predicts that particular families of planetesimals should be scattered inward at certain orbital phases. Suppose it predicts that fresh dust should become more likely during specific windows. If astronomers then watch the star and see increased dipping activity at those times, the connection between companion and debris would become much harder to dismiss. That would be the moment the system stops being a collection of coincidences. The giant would not merely exist near the dust. Its gravity would predict the dust. There are other possible victories. During a future deep dip, high-resolution spectra might reveal gas moving at velocities expected from infalling or evaporating bodies. Different chemical species could appear and change as the event evolves. Multicolor observations could track grain sizes in real time. Infrared measurements could test whether a fresh dust cloud heats up as it approaches the star. You would be watching destruction happen across more than 1,000 light years. Not as an image, as a changing spectrum, as a missing fraction of light, as atoms leaving fingerprints in the beam. And if that happens, the famous 20% dips would become less mysterious, not because they are less dramatic, but because we could follow the chain that produces them. A body changes orbit. It falls inward. It breaks. Dust spreads. The cloud crosses the star. The grains are pushed away. Then the system resets for the next arrival. That is the possible machine hiding behind Tabby's star. But we should also leave room for failure. Perhaps no future transit appears in any remaining window. Perhaps Gaia sees no compatible astrometric wobble. Perhaps radial velocities never strengthen beyond the tentative signal. Then the proposed companion may disappear from the story. That would not return us to 2015. We would still know far more than we knew then. The color dependence would still point toward dust. The later dips would still be real. The long-term fading would still require explanation. The known wide stellar companion would still shape the environment over long timescales. And the 2019 event would still demand another interpretation. Science does not move backward when a hypothesis dies. It removes one road. That is what makes the next few years so important. Tabby's star has reached a rare stage in a famous mystery. The newest explanation is not protected by vagueness. It is exposed. It has orbital windows. It has a predicted gravitational signal. It has an astrometric consequence. It can be checked. The mystery has become dangerous for the hypothesis. That is exactly where we want it. And maybe that is the most satisfying way to understand what has happened since this star first entered public imagination. The story did not travel from aliens to nothing. It travelled from a strange light curve to a physical system. At first, all we could see was absence. Light vanished. Then colour told us that some of the darkness behaved like dust. Infrared observations told us the dust could not simply be a giant permanent warm cloud. Later dips showed that the phenomenon continued. The known distant stellar companion showed that the system was not isolated. And now a smooth TESS event may have revealed another body much closer in, a giant planet or brown dwarf massive enough to reshape the orbits of smaller objects. One by one, shadows began to acquire machinery. That machinery may still be wrong, but it is testable, and that is more valuable than a perfect story. So what is hiding behind the galaxy's strangest star? Today, the most responsible answer is not a megastructure. It is not one giant comet, and it is not yet a confirmed planet. What may be hiding there is an architecture, a massive unseen companion, a distant stellar partner, reservoirs of smaller bodies, gravitational pathways that send some of them inward, and dust clouds that happen to cross our line of sight. The dramatic dips may be the visible surface of a much larger invisible system. You are not seeing the planetesimals themselves. You are seeing what happens after their orbits change. You are not watching gravity directly. You are watching the wreckage gravity leaves behind. And that is why Tabby's star remains extraordinary, even if every final explanation turns out to be completely natural. Nature does not need to build a machine around this star. Gravity can build one by accident. A distant companion pulls. A giant world scatters. Smaller bodies fall. Dust blooms across the light. Then, more than 1,000 years later, those missing photons reach us. For a few hours or a few days, the star seems to disappear. And inside that darkness is a record of events we never saw happen. The next transit may tell us whether the hidden giant is real. The next wobble may reveal its mass. The next dusty dip may show us the debris it helped create. And if those clues finally lock together, Tabby's star will not become less strange. We will simply understand what kind of strange it is. Until then, the galaxy's strangest star is still keeping one piece of its machinery in the dark.